Hello, everybody. My name is Ben Green, and together with Professor Panos Papazoglou, I'm going to be lecturing this course A2 Metric Spaces and Complex Analysis. So we've divided the course up into the metric spaces part and the complex analysis part separately. The division is roughly 1/3 to 2/3. So the metric spaces part of the course is approximately 1/3 of the course as it's usually lectured. Now, of course, things are a bit different this year, so we're not lecturing things in 1-hour chunks. And what I've done with the metric spaces course is to divide it into 23 sub-lectures. And those vary in length from about 10 minutes to about 20 minutes, most of them in the kind of 15 to 20 minute range. Now, hopefully the way I've labeled them makes it obvious which lecture corresponds to which section of the notes. You will find full printed notes on the course webpage. And that, I think, is all I have to say on the matter. So I hope you enjoy these lectures and learning about the topic of metric spaces, which is a very beautiful and really fundamental topic in mathematics. Hello, so this is the first lecture of the metric spaces part of the A2 course. Now, in prelims, you studied the real numbers in some detail. And somehow the point of this course is to show that a lot of the notions that you introduce there, such as limit of a sequence, the notion of a function being continuous, really depend very, very little on the actual structure of the real numbers. And they can be put in a much more general context, and theorems proven about them in that much more general context. And this is a very, very useful thing. Before we come to that, let's just briefly recall what the real numbers are. So the real number is always denoted by a blackboard bold or a bold letter R. And let's just briefly run over some of their properties, which you covered in the prelims course. So the least upper bound property, every non-empty bounded subset S of the reals has a least upper bound, usually denoted by sup of S. And by definition, that's a real number C, which is an upper bound, so x is less than or equal to c for all x in the set S, and it's the smallest such thing. So if c primed is another number with this property, another upper bound, then c primed is at least c. Very similarly, any non-empty bounded subset of the reals has a greatest lower bound, usually denoted by inf of S. The real numbers have the Bolzano-Weierstrass property. Any bounded sequence of real numbers has a convergent subsequence. And any Cauchy sequence of real numbers converges. Now, I won't remind you right now what these, especially, for example, the notion of a Cauchy sequence. We'll be talking about that in quite a lot of detail later on in the course in a more general context. But you might want to just go and remind yourself of the precise notion of a Cauchy sequence now. Now, just one little aside, in the prelims course, you talked about the real numbers, but I'm not certain that you were ever shown that the real numbers exist. And in fact, maybe it wasn't even mentioned that it's not obvious that they exist. And it really isn't obvious that the real numbers exist. And I'm not going to prove that they exist in this course either. But for those of you who are interested, I would certainly encourage you to read up on this situation, that the real numbers, which you've known since you were a child, which have all these nice properties, it's not at all obvious mathematically that they exist. So I've given some pointers in the notes to where you can read up on that a little bit more. But for this course, we'll just assume that there's this nice object called R, the real numbers, which satisfies all of these properties here. Now let's recall the definition of a continuous function from R to R. So if f is a function from the real numbers to the reals, we say that it's continuous at a point A if the following is true. For every epsilon greater than 0, I can find a delta greater than 0, such that if the distance from x to a is less than delta, then the distance from f of x to f of a is less than epsilon. Now that's a definition that you know well. But if you look at that, when I said that definition, I never used anything specific about the real numbers other than the word distance. So all I need to state the definition of a function being continuous at a point is a notion of distance. And that is what this part of the course is all about. So we're going to look at a very general concept of distance. So now we're going to come to the most important definition, the definition of metric space. So metric space is a set X together with a notion of distance on that set. So formally, it's a function from x cross x to r. So it's a function d from x cross x to r. D is going to measure the distance between 2 points. And it's going to have the following properties. And the list of properties is just all of the properties that you would want a natural notion of distance to have. So the first property is positivity. The distance between any 2 points should be non-negative. So if x and y, little x and little y, are 2 points in big X, and the distance from little x to little y is greater than or equal to 0. And moreover, the distance between 2 points is only 0 if they're the same point. So the distance between little x and little y is 0 if and only if little x equals little y. Okay, so that's a very natural property for a distance to have. Second property is symmetry, that the distance from little x to little y should be the distance from little y to little x. And then finally, the triangle inequality. So if I've got 3 points, little x, little y, little z, in big X, then they satisfy this inequality, that the distance from little x to little z is less than or equal to the distance from x to y plus the distance from y to z for any 3 points. So these are, if you're going to call something a distance, I think it's quite natural that you would require it to have these 3 properties. So we'll give lots of examples in subsequent lectures. But I mean, the most obvious example of a distance beyond just the usual distance on the real line would be the distance on the plane, for example, on r squared. So again, just the Euclidean distance between 2 points satisfies these properties. And we'll see more about that as well subsequently. So if you want to be formal, the pair x and d consisting of a set x together with a function d satisfying these properties is called a metric space. And that's the key object of study in this part of the course. Now, usually it's best not to be quite so formal as that. And so often when you're talking about a metric space, you just say x rather than the pair xd. And it's understood that when you see the letter d appearing in a proof, for example, it's the distance on x. So that's a very common convention, a little abusive notation. On a few other occasions, it's actually necessary to be slightly more formal. So, for example, sometimes we'll have 2 metric spaces with underlying sets x and y, and to make it completely clear which distance we're talking about, we might refer to the distance on x as d sub x and the distance on y as d sub y. And we'll see some examples of that later on as well. So that's the definition of a metric space. It's not a hugely complicated thing by itself, but to get a feel for it, one needs to look at lots of examples, and that's what we'll be doing in the next lecture. But before looking at any examples, let's prove a little theorem with this. So the triangle inequality implies something called the reverse triangle inequality. And this turns out to be quite useful. So this is the following lemma. Let's take points x, y, and z in a metric space. Then the absolute value of the distance between x and y minus the distance between x and z is at most the distance between y and z. And let's look at the proof of that. So this is really two inequalities because of the absolute value sign on the left. So we need to show that if I look at the expression inside the absolute value sign, so d of xy minus d of xz, I need to show that that's less than or equal to the right-hand side, and that minus that is less than or equal to the right-hand side. So I need to show the inequality that d of xy minus d of xz is less than or equal to d of yz, and the inequality that d of xz minus d of xy is less than or equal to d of yz. But actually both of those are just instances of the triangle inequality. So in fact, they're both just completely equivalent to the triangle inequality. They're just the triangle inequality with the variables switched around slightly. So that's a really basic lemma about metric spaces, but quite useful one. Okay, so that's the end of the first lecture. In the next lecture, we'll have a look at a large number of examples of metric spaces. Okay, this is the second lecture of the A2 metric spaces course. And in the first lecture, we gave the definition of a metric space. In this lecture, we'll go over some examples of metric spaces. Now, as I mentioned in the first lecture, the most familiar example of a metric space is probably the real numbers. So the underlying set X is the real numbers R, and the distance between X and Y is the absolute value of X minus Y, the usual distance on R. Now, what about R to the n, where n is a positive integer? Well, actually, there are several different possible choices of a metric on R to the n. So I mentioned three. If V is an element of R to the n, I'll write its components v1 up to vn. So I'm thinking of V as a vector with components v1 up to vn. The d1 distance between vectors v and w is the sum from I equals 1 to n of the absolute value of vi minus wi. So that's the d1 distance. We've then got the d2 distance, which is the usual Euclidean distance, which is the sum of the squares of the vi minus wi's, all of that square rooted. And then we've got what I call the d infinity distance, which is just the maximum over I equals 1 to n of the absolute value of vi minus wi. So those all have names. They're usually called the L1, the L2, and the L infinity distances, respectively. Now, are they all obviously distances? Do they satisfy the axioms of the metric space? Well, it turns out that actually the less familiar one, d1 and d infinity, is actually very straightforward, and I'll leave it as an exercise to show that those distances satisfy the axioms of the metric space. But the most familiar one, d2, the Euclidean distance, is a little less trivial to show that it satisfies the triangle inequality. So let's just go over why that's true. So for that, we need to talk about the Euclidean norm. So the Euclidean norm, which also known as the L2 norm, so norm of V in L2, is the sum of the squares of the VI's, of the components of V, all square rooted. And that can also be written in terms of the Euclidean inner product. So if I define the inner product of V and W to be the sum of VI WI, then the norm is the square root of V inner product V. And it turns out that the triangle inequality for the Euclidean distance D2 follows very straightforwardly from this property of the Euclidean norm, which is actually one of the axioms of what it means to be a norm, something we'll discuss in a bit more detail in the next lecture. But for now, I'm just using the word norm as just a word. Anyway, so the lemma is that if x and y lie in R to the n, then the norm of x plus y is bounded by the norm of x plus the norm of y. So the proof of that is to square both sides. That's equivalent to what we're trying to show because both sides are non-negative. So you square both sides and you get the expression that I've written here. Norm of x plus y squared is bounded above by norm of x squared plus twice norm of x, norm of y plus norm of y squared. Now the left-hand side here, norm of x plus y squared, can be expanded as an inner product of x plus y with x plus y. And because inner products are bilinear, I can write this as a sum of 4 terms. It's inner product of x and x plus inner product of y and x plus inner product of x and y plus inner product of y and y, which is the norm of x plus the norm of y plus the contribution from the 2 cross terms, and they're both equal to the inner product of x and y. So I get that the norm of x plus y squared is equal to the norm of x squared plus the norm of y squared plus twice inner product of x and y. So if I compare this with the preceding line, I see that what I need to do to prove the lemma is just show that the inner product of x and y in absolute value is less than or equal to the norm of x times the norm of y. And that is a well-known inequality called the Cauchy-Schwarz inequality. So this lemma, this fact that the Euclidean norm satisfies this inequality, is very closely related to the Cauchy-Schwarz inequality and follows fairly easily from it. Now, why does the lemma imply that d2, the Euclidean distance, is a distance? Well, that's quite straightforward. So let's just prove that. The triangular inequality for the d2 distance is the following statement. So we need to show that d2, the distance of u and w, is bounded above by the d2 distance between u and v plus the d2 distance between v and w. And that's equivalent to the statement written here, so that the norm of u minus w is bounded above by the norm of u minus v plus the norm of v minus w. And that is just the lemma I've just proven under a simple substitution. So substitute x equals u minus v and y equals v minus w into the lemma on the last slide, and you immediately get this statement. So the Euclidean metric really is a metric. The proof that the triangular inequality holds is not trivial and is essentially boils down to the Cauchy-Schwarz inequality. Let's talk about something completely different, the discrete metric. You can define a metric on an arbitrary set in the following manner. Let x be any set and define the distance between points x and y to be 1 unless x is equal to y, in which case you define the distance to be 0. So it's very straightforward to check the axioms of a metric space, and this is always a metric. It behaves quite differently to the familiar metric on the real numbers, and if you're formulating any question or trying to do an exercise on metric spaces, this would be one of the basic examples that you look at to see if the answer should be yes or no to your question. Now, as a number theorist, I'm very fond of these metrics, the p-adic metrics. So we'll take the underlying set to be the integers z, and I'm going to talk about what's called the 2-adic metric, but you can do the same construction for any prime p in place of 2. So I'll define the distance between x and y to be 2 to the minus m, where 2 to the m is the largest power of 2 dividing x minus y. Okay, so for example, the distance between 1 and 5 is a quarter, because 5 minus 1 is 4. That's divisible by 4, but it's not divisible by 8. So the positivity properties and the symmetry property of the metric are very easy to check. And the triangular inequality also holds, and in fact a stronger statement holds, known as the ultrametric property. In fact, the distance between x and z is bounded above by the maximum of the distance between x and y and the distance between y and z. So that certainly implies the triangular inequality because the max is less than or equal to the sum. And that in turn is really just a rephrasing of the statement that if 2 to the m divides both x minus y and y minus z, then 2 to the m also divides x minus z, because x minus z is the sum of x minus y and y minus z. So this 2-adic metric looks very, very, very different to the usual Euclidean metric. So for example, the distance between 999 and 1000 is 1, but the distance between 0 and 1000 is actually 1/8, because 8 divides 1000 minus 0. So these come up a lot in number theory, and they just look very, very, very different to the Euclidean metric. There are a few examples on the example sheet like that. Let's go over another few examples from different areas of maths, just to show how ubiquitous this notion of a metric space is. So in graph theory, some of you may know a little bit about graphs. There's a whole course on graph theory next year. So if you've got a graph G, so that is to say a finite set of vertices V joined by edges. So suppose it's a connected graph, by which I mean that between any two pair of vertices there is a path joining those vertices. Then you can define a distance in the following manner. Declare the distance between a vertex V and itself to be 0, and the distance between two non-equal vertices V and W is the length of the shortest path from V to W. And then that's a metric. So let's briefly talk over why. So the symmetry property, if you've got a path from V to W, then you can get a path from W to V just by backtracking, reversing down the path. And the triangle inequality, if you've got a path from U to W and a path from W to V, well, that automatically gives you a path from U to V, whose length is at most the distance from U to W plus the distance from W to V. Now, there might be a shorter path that doesn't go via W, but certainly that is a path from U to V. Very important example of a metric comes up in group theory. If you've got a group G, and if it's generated by elements A and B and their inverses, so every element in the group is a finite product of A, B, A inverse, and B inverse, you can define a distance in the following manner. The distance between V and W is the smallest k, such that I can write V as W times a product of k things that are either A, B, A inverse, or B inverse. So this is called a word metric. So I'll leave it as an exercise if you're interested to check that this really is a metric. It's actually very, very closely related to the path metric, the previous example. In fact, given a group generated by some elements, you can define a graph in such a way that this word metric coincides with the path metric. And then another example from a different area of maths. This one comes up all the time in theoretical computer science. So we'll take the underlying set X to be 0, 1 to the n. So that's all strings of n zeros and ones, known as the Boolean cube. And then you can define the distance between X and Y to be the number of coordinates in which X and Y differ. So the number of zeros that you'd have to flip to ones or vice versa to get between the string X and the string Y. So that's called the Hamming distance. And that's a vastly important notion of distance that comes up in theoretical computer science. And finally, we'll mention one from geometry, projective space. So P of R to the n, this is the set of lines through the origin. So directions through the origin. And then you can define a distance on projective space in the following manner. So the distance between two lines L1 and L2 is defined to be the square root of this expression of 1 minus the ratio of the inner product of V and W squared over the Euclidean norm of V squared times the Euclidean norm of W squared, where here V and W are any non-zero vectors in the line L1 and L2 respectively. But because of the homogeneity of this expression in V and W, it doesn't matter which representatives V and W you choose from the respective lines. It won't change the distance, and so this really is a function of the lines and not of the V and the W. So I'll leave it as an exercise to prove the triangle inequality for this. And another exercise is to show that when n equals 2, so this is lines through the origin in the plane, this distance is just sine of the angle between the lines. So we've seen examples of metric spaces arising in all sorts of different areas of mathematics. It's a ubiquitous object.